Hello, everyone. My name is Jacob Weightman. I'm a compiler engineer at RISC Zero. And today I'm going to be talking to you about Zirgen, our new DSL for writing efficient ZK Stark circuits. First, a little bit of context about RISC Zero. We recently announced a new network called Boundless, which we envision as sort of the full stack solution for zero-knowledge application developers. So this is everything from how you actually get your zero-knowledge proofs on-chain for use in real applications, all the way down to the zkVM layer where the execution actually happens. So today we're going to be zooming in on that zkVM layer as we're talking about how circuits actually get built at RISC Zero. So back in the old days of ZK, applications were built with custom circuits per application, and you would pass in some sort of input and you'd get your proof out at the end. The primary innovation of the zkVM model is that application-specific circuit gets replaced with a general-purpose circuit that implements a general-purpose architecture. At RISC Zero, that is RISC-V. So now the program itself becomes part of the input, such that when we want a proof, we can just hand it a program written in a conventional language compiled with something like the Rust compiler or anything that works with LLVM, along with the input, and get our proof. But in pursuit of higher performance, it seems ideal to have some additional accelerators. So in parallel, or in sort of analogy with the way that conventional software engineering works, where you write a program in a general purpose language and run it on a general purpose CPU, over the last few decades, we've seen the emergence of heterogeneous computing, that it's beneficial to offload intensive computations to specialized hardware that can do them faster, things like GPUs, FPGAs, DSPs, things of this sort. And so the model that we're pursuing here is to have our general purpose RISC-V CPU in this model, as well as a series of accelerators for specific operations that we could do a little bit more cheaply with a custom circuit. These are things like accelerators for the catch-check hash function or alternate commitment schemes, elliptic curve operations, things like that. So when you go to do a proof on RISC Zero, typically it's useful to have sort of unbounded duration of computation. And so in a Stark-based proof system like ours, we have to subdivide this into fixed size segments. But after we've done that, we can roll them up together with recursion. And so the traditional picture of what you can do today without accelerators looks like this. Now, when we introduce accelerators, the picture stays pretty much exactly the same, except that the third line here changes. We can swap out some of these segments with accelerators and roll them up in exactly the same way to a single succinct proof. So with this in mind, right, this architecture calls for a lot of different circuits. We have the zkVM itself, which implements RISC-V. We have a recursion circuit that is able to verify these receipts, as well as an unbounded number of accelerators that might be useful to plug into different applications depending on the application developer's needs. And so with all these circuits, it would be really ideal to have a really great experience when designing these in order to be able to effectively design, implement, test them, and be confident that they're secure and efficient. So it turns out, though, that a lot of the ways that people have written Starks comes with a lot of drawbacks. In particular, each of these drawbacks comes with an opportunity to do something better. So one thing that we saw was that a lot of Stark description languages really split out different parts of the implementations. You have separated constraints from witness generation, and it's all separate from, for example, the logical structure of the circuit that you might use to achieve some notion of composability when writing your circuit. The other is that composability options are often quite limited. And so it would be really nice if we had the ability to describe a small fragment of our circuit and then glue these pieces together and test them independently and do all of those things that we get to do in traditional software development. And lastly, there's a lot of boilerplate and complexity that comes along with writing circuits. For example, for every circuit that we wrote, we found ourselves re-implementing things like permutation arguments and lots of other things of that sort. So let's zoom in and look at some real Zirgen code and see what it looks like. So we have a single concise representation that captures everything of interest here. So for example, let's take this bitreg component. It's going to take as input a value called x. It's going to write into a register. A register is an abstract view of a column in the Stark trace. This reg component comes along with an implicit constraint that that register value is equal to x. Then we go ahead and add another constraint here. So this polynomial is satisfiable if and only if r is equal to 0 or 1 in order to make these terms 0. And lastly, we return this value r. This is not exactly a return statement, but it's quite similar. And it indicates that this bitreg component can, in any context, be used as if it is a register, that register r in particular. So you can kind of see how we've commingled all of these things together into this very short representation. Next, let's talk about composition. So you see here implementations of 4 distinct combinational logic gates that you'd see in traditional hardware design, right? You can negate a bit register by subtracting its value from 1, because 1 minus 1 is 0, which is not 1, and 1 minus 0 is 1, which is not 0. And similarly. So you could go in and check all of these expressions, but the thing that I want to call out here is that we have this very nice, almost functional sort of composition that you can do with this. The other major type of composition that we have in the Zirgen language is called a mux, or a switch, where we can multiplex over a set of selector values. So with this component, full adder, we're implementing a add with carry component using the components that we just composed out of bitreg in order to do a 1-bit adder with a carry in, C, and a carry out. So the sum should be true if at least if an odd number of x, y, and c are true, that is, our sum is 3 or 1, which can be done in this way, which should be a familiar expression for people that have studied hardware implementations of adders. And the carry bit should be true if at least 2 of them are. So we do this by cases. If c is true, that is, c is 1, then this selector becomes the array 1, 0. And so this first mux arm becomes active. So if c is true, then we only need x or y to be true for the carry bit to be set. And if c is not true, we need x and y to be set for the carry bit to be set. In fact, when I look at this, I actually think it feels a little bit simpler than the combinational logic expression to do this in traditional hardware design. There's a lot of other niceties that sort of come with this that are a little bit harder to fit in slide-sized examples. But one of them is that permutation arguments are built into the language. That is, you can simply declare a component with the argument keyword, and we will automatically synthesize a logup sum for it in order to do a logup style permutation argument, and all of the layout constraints that come along with that will be implicitly enforced. Similarly, we have an abstract way to describe the structure of a circuit, which enables this sort of composition. That is, you can abstractly describe the logic of the circuit that you want without having to bother with the particular column offsets or how things are precisely arranged in the concrete Stark implementation. And then the compiler can go and generate an efficient layout using a constraint solver at compile time. Lastly, it has some built-in facilities for testing, such that you can write unit tests, integration tests, whatever you feel like, directly alongside your circuit implementation, which ends up saving a lot of work and eliminates the need for test harnesses and extra tooling in order to test fragments of a larger circuit. Now, you might be thinking maybe this comes with some significant performance trade-offs. That is, we're losing a lot here by accepting all of this abstraction. And it turns out that that's not entirely true, in the same way that most of us don't write assembly anymore. If we want to do low-level programming, we write something like C or even Rust with some extra restrictions. So in particular, there's a lot of room to optimize circuits with this representation because we have so much information about the structure of the circuit in this approach. For one, we have all of the traditional compiler optimizations that you might think of when you think of a C or a Rust compiler even, you get constant propagation, dead code elimination, common subexpression elimination, and all things of that sort, as well as some more circuit-specific things. So in particular, there are some layout optimizations that can be done automatically. For example, if you were to generate 2 separate registers that are constrained to be equal, you can coalesce them such that they land in the same actual column of the execution trace, which saves you a register. There's also a lot of room to do optimizations directly on the constraint sets. For example, if one constraint implies that another constraint is satisfied, that second constraint can be eliminated altogether. And so it turns out that there's a lot of things that can be optimized to get us pretty optimal. So Zirgen was released as open source software just last month. And we have a couple of exciting things coming up for it. In particular, we have some accelerators in the works written in it, namely a Ketchak accelerator to speed up proving of Ethereum, among other things. And we're also excited to provide some better support for users of the RISC Zero platform to write accelerators for the operations that they care about, even if we haven't written accelerators for them ourselves. And lastly, there's also an interesting opportunity here to use compiler tooling to assist formal methods on circuits. So you could think about doing things like emitting a lean specification from the actual source code, or based on the circuit definition, or even doing things like emitting the constraint set in a format that would be amenable for consumption by a tool like Picus to do determinism analysis. Ultimately, we're not entirely sure what we're going to pursue in this vein, but there are a lot of opportunities for this. So with that, I'd like to invite you all to check out the website for Boundless, the new RISC Zero network, as well as to check out the Zirgen open source repository through the QR code on the right. Thank you. It's 4:10. I think we have 5 minutes for questions.
Okay.
Thank you for the great talk. What are the current backends that you have? I guess, first question.
Yeah, so are you asking what proof systems we support?
Well, I mean, like, I don't know, Plunky 3 or whatever else.
Yeah, this is purpose-built for our own proof system. So RISC Zero has its own Stark-based prover, and it targets that.
Are there any plans to support other ones or make it configurable somehow?
Well, it's open source, so we would certainly be amenable to people contributing that. I don't think RISC Zero is likely to invest in that.
Okay. Thank you.
Questions?
Yeah, thank you. If I recall correctly, there was a talk in ZK Proof 5 that was talking about Zirgen, but I think it was a product that was very different. It was more about backwards compatibility with the circuits, if I recall correctly.
Yeah, so Zirgen was the old internal to slightly external name for this compiler infrastructure, and that name was largely used to describe sort of an earlier version of that, where we were really only doing the compiler-based, like traditional compiler optimizations on custom intermediate representation for the circuit. So the language front end is totally new, as well as most of the optimizations. So that's what we've been working on for the last 2 years.
Yeah, thank you.
Yeah. I think we had another question here on the left.
Thank you for the talk. It's just what kind of constraint optimization techniques do you plan to apply?
Yeah, so one in particular that's really obvious is if you have 2 identical constraints, you can prune one of them. One that's a little bit less obvious but not hard to explain is that if you had a constraint like x times x minus 1 times x minus 2 equals 0, and another constraint like x times x minus 1 equals 0, yeah, one of them is implied by the other. That's the kind of thing that I'm talking about when I talk about that.
Any other questions?
So do you allow to write your own like precompiles in a sense, like can I write my own Ketchak implementation, for example, in this language?
I'm not sure I heard the question.
Do you allow to write your own kind of precompiles in a sense with this language?
You as a user of RISC Zero?
Of Zirgen, yeah.
Yeah, it's not well supported right now, but that is on the roadmap. Yeah.
Okay. Thank you again, Jacob.